the conformal field theory and the bootstrap.
Okay, well, this was very unexpected, so it's going to be very informal and improvised in a sense. And, well, the success also relies on you interrupting me and guiding me in which direction I should take. So, so Wilson gave us this beautiful language to talk about quantum field theories, you know, to draw pictures like that. You know, you have some fixed points and they're connected by some RG flows. So that's how we think about quantum field theories. And we think about it daily in terms of these pictures. And this has a marked contrast, this daily use of this language, with how little we can do rigorously. And with how little we can do quantitatively. Because these fixed points, now let's take the Ising model, the 3D Ising model. So there is presumably some fixed point, you know, there is some CFT which describes the 3D Ising model, and you can presumably flow to this CFT from Gaussian fixed point. But what do we know about this fixed point? I mean, it's a Platonic object. It exists in some Platonic sense, but we cannot touch it, we cannot compute anything with it, and it's very disconcerting. And you know, my interest in this conference is, I would like to learn because I think that something has to be done about this problem. But in the meantime, so there is this bootstrap approach, which is an attempt to leapfrog this difficulty, and an attempt to try to think about fixed points, about CFTs, directly in isolation, without any microscopic origin, without any RG, without any, and try to distill some set of rules which these fixed points obey, which could perhaps allow to get at them, to compute something about them, to classify them, while waiting for a more general theory which will eventually connect them with RG flows. So what are these rules? What are these axioms which we distill from various sources? But okay, eventually they have to be proved. But for the moment, I'll try to motivate them. So the first kind of crucial axiom is that we have to focus on local operators and correlation functions of local operators. So we are going to think, so we're going to consider some CFT which lives in D dimensions. And you know, D can be 2, but you know, the most interesting case is, the hardest case is D equals 3 or 4. And in this theory, we are going to consider some local operators, and we are going to consider their correlation functions. Something like that. And these correlation functions, they can be thought of as something coming from a lattice model where you go to the critical point, you go to the large distances where everything becomes scale invariant. Then you throw out all the irrelevant decaying terms, so you just keep the scale invariant part, which is at long distances, but now you extrapolate it to all distances from 0 to infinity, so you get a function which is defined at all distances from 0 to infinity, positive distances, so you never look at what happens at coincident points in this approach, at least not necessarily, and so you study these objects. So there is no random field, there is no probability theory here, they're just functions of real variables, finite functions. Okay, and so what do we know? So what do we know about these guys, these local operators, we call them, these labels, OI? Well, there is a very important physical idea that we would like to keep. So there is no we cannot prove it rigorously, but it helps a lot to understand what's going on in this field. So I would like to explain this idea. So even though we throw out all this random field stuff and we pretend that we don't need it, there is one place where we kind of need it to think. And this is the idea that we would like to think that if you take one of these local operators, so O of x, and you consider correlation function where all other operators are somewhat separated from this one, and you surround this operator by a sphere, as d minus 1, of arbitrary radius, we would like to think that this operator creates on this sphere, so when you insert it in correlation function, we can kind of excise the interior of the sphere and replace it by some sort of state of the field of whatever fields which this theory has, which live on this sphere. So we would like to keep this very powerful idea about path integrals, that you can slice them, you can cut them and glue them and reglue them and so on. So that's something that that is needed in order to understand the axioms which follow. But once we arrive at the axioms, we can forget about this. But you know, I think this physical idea is clear, so let's keep it.
That's basically some form of locality.
It's some form of locality which the theory knows about. Yes.
So is this like what people like to call the spatial Markov property?
I never heard it called this way, but yeah.
It should be sort of.
Yeah. But some, and now if I start inserting more operators inside this sphere, then I will, the way the language that we use, when you insert more operators, O1, x1, O2, x2, then we just change the state that these operators produce on the sphere. Now this looks very much like the classical Osterwalder-Schroeder construction of the Hilbert space of the theory, starting from operators, correlation functions which inserted on one side of the plane, except that here in scale invariant theories it's nice to use spheres and not planes. Okay, so that's an important point. Now this important point leads to a concept of operator product expansion, which is another key idea, OPE. By the way, all these axioms have been understood basically in late 60s and beginning of the 70s. So all these ideas have been around. So this new revival of this approach basically amounts to picking out of the huge amount of ideas that people proposed over the years, the ones which are correct, and discarding the ones which don't work. That's the non-trivial part. So the OPE, once you buy this, it's very easy. You just say, well, you know, let me assume, OPE is a form of completeness relation. Let me assume that I know all my local operators over here. I just picked out a set of operators, and this is the whole set. Then, you know, every time I insert a local operator, I produce a state on the sphere. So when you insert two, if I wrote down the whole list of operators, then it means that I know how to produce any state on the sphere. Because if I take a sphere, in the scale invariant theory, I can shrink the sphere to a point, and this becomes a local operator. So any state on this sphere, I can shrink to a point, and it becomes a local operator. This is called state operator correspondence. So now let me take two operators inside the sphere. So O2, O1. They produce a state, but since I know all of my states are in one-to-one correspondence with operators, this state O2, O1 can be expanded with some coefficients which I don't know, but they exist. And they depend on O2, O1, X1, X2 in operators inserted at the origin of the sphere. So this is called OPE. So this expansion exists. And since this is expansion between states, it means that it's valid independently of what I inserted outside of the sphere. So as long as there exists a sphere which separates these two operators from everything else, if I know this coefficient ck, I can replace these two operators by this series inside of any correlation function. This is an axiom in this approach. So far, I did not say anything about conformal invariance. Conformal invariance is, there are various ways to understand why it emerges. So conformal invariance is a beautiful symmetry because it emerges. It's the most powerful emergent symmetry. It emerges in the infrared, emerges at the critical point. So why does it emerge? There are various ways to understand it. One can try to understand it from the RG point of view, because you can view an infinitesimal conformal transformation as a sort of non-uniform RG transformation, where you vary this step, the rescaling step of your lattice. That's intuitive, but that's definitely non-rigorous. The most powerful way to understand why conformal symmetry emerges is to try to reduce conformal symmetry to existence of a very special operator among this list of operators, which is the stress tensor operator. So it appears that any critical point of a theory which is described on the lattice by a local, for example, next to nearest action, next to nearest Hamiltonian, contains this special operator T mu nu of x, which satisfies two rules. So first of all, it's conserved. So all its correlation functions are conserved. And okay, it has scaling dimension exactly d, and it's traceless. Now, there are some extremely special situations where the stress tensor exists, but it's not traceless. In this case, the critical theory is not going to be described by a conformal field theory. It's going to be a scale invariant theory which is not conformal. So such cases exist, but all known cases correspond to Gaussian theories. So there is some genericity argument that I'm not going to explain that tells you that basically, generically, you expect that T mu has to be equal to 0. So the existence of this stress tensor is somewhat of a mystery. So it's not, it's not very well rigorously understood. There are various blah blah arguments, but I'm not going to describe them. So in cases where mathematicians can prove conformal invariance, like in the work of Smirnov, for example, they don't follow this path. They don't follow neither this path nor RG path, but they find a shortcut or a detour through discrete analyticity. That's kind of cheating. And it also implies that they can only treat very special lattices, a handful of models, and only in 2D. So it would be nice to have a better understanding of this. But if you buy that T mu nu exists at the critical point, then you can show that correlation functions have to be conformally invariant. And the kind of argument that you do is you take a correlation function of a bunch of operators, you surround it by a sphere, and on this sphere you integrate against T mu nu times some field, times some vector field. So you can see this kind of integral, d sigma nu. So if T mu nu is conserved and epsilon mu is a conformal killing vector field, then you can move this sphere around and this integral does not change. So you can particularly push it to infinity and then the result is 0. Or you can move it and you can surround each operator with a small sphere. You can kind of deform the sphere into small spheres. Then you use OPE of T mu nu with each one of these local operators. And you can argue that, the result of this operation is to show that your correlation function does not change under some small infinitesimal conformal transformation. So this is kind of arguments that we use daily in physics. So what does this mean in the end? It means that each of these local operators, it transforms in a representation of conformal group in d dimensions. So it means that there is a rule that tells you that if you apply conformal transformation from x to x prime, and so you have a correlation function of, if you have a correlation function at points O1 x1 or n xn, and you have the same correlation function at points x1 prime or n xn prime, they are related in a very simple way. So they're not exactly equal, but they are related by some factor, by some local factors, lambda x1 prime to the power delta 1, lambda of xn prime to the power delta n, where these lambdas are local. So conformal transformation at every point that looks like a rotation and a dilatation. So this lambda is the dilatation factor associated with every point.
Could you end up having also some kind of non-trivial transformation with the O's themselves? I mean, they could be things more like vectors or something.
Yes. So if O's have indices, then, as I said, conformal transformation is a dilatation times rotation. So dilatation acts like this, and rotation or ON, SON rotation matrix acts on these indices in a natural way. So this is a rule, and operators which transform, whose correlation functions transform according to this rule, are called primary operators. And every operator is either a primary or a derivative of a primary. Now, this classification applies if space-time dimension is 3 or 4 or higher. In d equal 2, there is a finer classification that I don't want to go into, because the conformal group in 2D is larger.
Isn't there an inversion?
So there is a special transformation, which is the inversion transformation, which is disconnected from the unit transformation. So whether the theory is invariant under inversion or not is not automatic. Basically, if the theory is parity invariant, then it's going to be invariant also on the inversion, because inside conformal group, inversion is conjugatable to parity. So most theories are also invariant under inversion, but not all.
This OP assumption you make as an identity requires scale invariance?
That requires scale invariance and locality.
Not necessarily conformal.
Not necessarily conformal invariance. But now, if you have both OPE and conformal invariance, you can ask that these two assumptions have to be consistent with each other. And this turns out to be extremely powerful, and it allows you to fix these coefficients ck, most of them, up to a handful of real numbers. So basically, what happens is that, so as I said, in a conformal theory, every operator is going to be either a primary or a normal or a derivative of a primary of a certain order. Now, in the right-hand side here, all operators should appear, primaries and their derivatives.
So what are those primaries?
Primaries are operators which cannot be represented as derivatives of someone. For example, if you take the lowest dimension operator, it's bound to be a primary. if you take stress tensor is a primary. So concretely, in the Ising model, the spin field of the Ising model is going to be a primary, the lowest, because it's the lowest operator in its symmetry class. It's odd under the Z2 symmetry. And the energy operator, it's the lowest operator, which is even, so it's also going to be a primary. So.
But the primary operators transform homogeneously.
Homogeneously.
And the non-primary ones don't have an inhomogeneous.
Yes. So their transformation rules followed by differentiation. Yeah. So this, by the way, I just wrote a review article with Alessandro Vicky and David Polland that you can find on the archive. It's like a 100-page article for reviews of modern physics. And it contains a big section, a motivational section, and all the results. So coming back to this, so these coefficients Ck, in the scale invariant theory, there's not much you can say about them. But in a conformal invariant theory, you can relate the coefficients of a primary and the coefficients of its derivative. So the way you can write this conformal OP, so conformal OP looks like O1 of x1 O2 of x2 equals sum over primaries and okay, so you introduce these numbers lambda 1 to k which are called OP coefficients, and here you have let me write it like this. Let me write here a function p which depends on x1 minus x2, and it's a power series in derivatives, and it acts on the primary operator OK of y, and here we can have to put like y equals 0. So the important point is that this whole beast P, it's completely fixed by conformal invariance. In terms of what? In terms of scaling dimensions of these operators delta 1, delta 2, the scaling dimension of this guy delta k, and the space-time dimension d, space dimension.
P depends on K or no?
P depends on k, yeah. So, but it only depends on these parameters, on delta 1, delta 2, d, delta k. It's computable. It's just some special function. And so now we're done in the sense that we know all the parameters which characterize conformal field theory. So these parameters are spectrum, which are these numbers delta I, and also, as Martin noticed, we also have to say how all of these guys transform under the rotation group, how many indices they have. So there is also some representation, SOD representation, rho I, scalar, vector, and so on. And these coefficients, lambda ijk. So if you know these two sets of numbers, then you know everything, because you can compute any correlation function of your theory by repeatedly applying this OPE. Well, I did not say one thing. What I did not mention is that so it's clear that if you apply OPE, then you reduce n-point functions to n-1 point functions and so on. But then you have to stop somewhere. So where do you stop? You stop that you can stop either at the level of a 1-point function, because the 1-point function of the unit operator is 1, and the one-point function of any other operator is 0 for dimensional reasons. Or you can stop at the level, if you don't want to go all the way to one-point function, you can go you can stop at two-point functions. And the two-point functions of any operator with itself is completely fixed by conformal invariance. So it's equal to some tensor structure which depends on the representation of this operator on rho I, divided by x minus y to the power 2 delta I. So you reduce, and you normalize operators in such a way that the coefficient here is 1. So it's just a choice of normalization. So in this language, to solve conformal field theory is just to determine these infinite sets of numbers, delta I and lambda ijk.
So do you have these pk's?
Yeah. There is an explicit expression for them. Yeah.
They're completely determined.
They're completely determined. Yeah.
Well, it's a power series, infinite power series.
It's an infinite power series. Yeah. So pk is an infinite power series. So there are some convergence issues here which can be addressed to some extent. So many CFTs of interest to statistical physics and all CFTs of interest to high energy physics are unitary, which means reflection positive in Euclidean signature. And in those CFTs, using reflection positivity, you can show that various series which appear at various points of this program, for example, you take a 4-point function, you apply OPE, you get an infinite series. Does this series converge? So you can show that this series converges, and you can put bounds on how fast it converges. In non-unitary theory, there are many CFTs which are not unitary, and they are very interesting to statistical physics. And for those guys, this approach is on less of a firm footing, but at least in some cases it seems to work as well.
So, is that a statement that if you have reflection positivity, you can prove they converge?
Yeah. 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 Well, at least at the physics level of
Well, yeah, I understand.
yeah.
Isn't there even some sort of proof by Mach a long time ago?
There is some literature going back to Mach.
Axiomatic framework.
Yes. So in fact, this literature is being rediscovered by the new generations and inspiring us a lot and so on. So they were very much fixated on the Minkowski space in those days, while nowadays we kind of think from the Euclidean point of view. But miraculously, it was found that even if you are interested in completely Euclidean theories, like in the Ising model, at some point even from a practical perspective, it's useful to continue to Minkowski space and study certain things in Minkowski space. You see certain things much nicer in Minkowski signature. So some properties of this spectrum. So this spectrum and these numbers, they are kind of a bit of a phone book. So suppose somebody hands you this set of numbers, you can compute everything, but you don't understand what's this phone number.
But you never say what are these operators somehow, this O axis or.
So these operators, if you commit yourself to a lattice model, then these operators are some non-universal infinite combinations of your lattice operators. So if you take a lattice operator and you measure its 2-point function at large distances.
So what is lattice operator?
Like lattice spin. Let's take an Ising model on a lattice. Let's take spin at point 1 and some distant point r, and we are at the critical temperature. Let's measure the 2-point function. It's not going to be an exact power law. It's going to be an infinite series of power laws these power laws are the two-point functions of these operators OI. So the way we interpret this is that the lattice operator can be expanded in an infinite series of these scaling operators, and vice versa. But these expansions are non-universal. So in this approach, you say, I don't care about non-universal stuff. I only focus on universal information. So there are infinitely many of these numbers delta I. So in usual approach, in the RG approach to critical phenomena, most of these numbers you have never seen. You just seen like critical exponents, and what are the critical exponents? There's eta critical exponent, there's nu critical exponent, and then there's maybe omega, which is the subleading critical exponent. These are the ones that everyone has been talking about. So all these three critical exponents that are trivially expressible in terms of three of these numbers delta I. So eta is related to delta sigma, nu is related to delta epsilon, and omega is related to delta epsilon prime, to the subleading epsilon. But there are infinitely many other deltas, and which nobody has ever cared about. If you want to do this approach, you have to care about all of them. And you also have to care about lambdas. You cannot determine deltas without determining lambdas. Again, this is very different from the RG approach. In the RG approach, it's very easy to determine deltas if you know the fixed point. You just linearize around the fixed point, and then you see what are the exponents. That's what Antti explained. But lambdas from the RG approach, I mean, what are they? I mean, nobody. It's not clear that they carry any particular fundamental meaning. In this approach, they are as fundamental as deltas. You have to determine them together.
But I thought your deltas were primary, only primary.
Only of primaries, yeah.
But usually you have only finite number of primaries.
So so this is an important point. So if you are, so when I said that every operator is either primary or derivative of primary, it corresponds to certain grouping of operators. So I grouped operators in this huge multiplets, an operator and all of its derivatives. Now, if you are if you only do this grouping, there are always infinitely many primaries. However, in 2 dimensions, you can do a further grouping of operators using Virasoro algebra, which you can view as kind of, and then in some very special cases, after this additional grouping, you will end up with only finitely many multiplets. But these are very special cases. In most cases in 2D, even after this additional grouping, you still have infinitely many primaries. So there are famous cases like minimal models where you have finitely many primaries after this additional grouping, and they get a lot of attention because you can do things exactly and so on. It's nice and it's important. But there are gazillions of 2-dimensional CFTs. For example, take some CFTs of center charge larger than 1, about which the progress has been stagnating because exactly they contain infinitely many primaries, no organizing principle, and so what do you do about them? They're not exactly solvable. So
in 3 dimensions, you say always.
And in 3 dimensions, you're always in this bad situation. There are infinitely many primaries. There are infinitely many primaries, but there's also some sort of decoupling phenomenon. So the primaries of high dimension, they are the observable. For example, if you take correlation functions of primaries of low dimension, then it's not so sensitive about what happens to primaries of high dimension because of these convergence results. So when you take a series, and you can show that contribution of
now converges in K.
Converges in K, yeah.
So here you end up with a huge amount of constraints on these delta and lambdas by presumably wanting some sort of associativity.
Exactly what I was about to talk next. Yeah. Yeah. So there is some associativity constraint, and And this associativity constraint again is based on locality. So it's so you take a 4-point function of any 4 operators, and then as I said, every time we can surround 2 operators by a sphere, you can use OPE. So, but we can do it in 2 different ways. We can take a sphere which separates these 2 operators from these 2 operators, use OPE here and here, and then we get one expansion for this 4-point function. So we got sum over k, and we write it schematically like this. But this is not a Feynman diagram. What it means is that I took these 2 operators, used their OPE, these 2 operators used their OPE, and then I reduced everything to 2-point functions of the exchanged operator. But I could do it in a different way. I could do it like this, and I would get a different expansion. And these expansions, you can write it in a different way, and it becomes clear that this is a associativity constraint on the operator algebra. So this is what we call bootstrap equation. So you are supposed to, you can convince yourself that if you solve this constraint for all operators, then you don't have to consider higher point correlation functions. Such constraints are going to be satisfied also for higher correlation functions. 4-point functions is enough. And so these are quadratic constraints. So you have here lambda 1 to k, lambda 3 for k. So these are quadratic constraints on OPE coefficients which multiply these objects that I denoted by this symbol, which depend on coordinates x1, x2, x3, x4. So these are some functional relations, and they also depend in a complicated nonlinear way on all of these numbers, delta 1, delta 2, delta k. So it's a mess. It's a mess, and that's why for a long time people thought that it's not promising. Just looks too complicated. You don't know where to start and how do you solve this. Except in 2D, where you have finitely many, where you do the special cases where there are only finitely many things, then then it becomes a finite dimensional system, and you can find solutions. And at least from these solutions, we know that this works. This was what was done by Belavin, Polikov, and Zamolodchikov in '83. But yeah, what to do with higher dimensions, it was not clear.
Is there any reason why to restrict this operator product expansion only on pairs, not in triplets or things like that? There's no deep reason. Yeah, there's no deep reason. So the logic by which I described OPE, I said, okay, you take 3 operators and it has to be expandable because of the state completeness. It would work also for 3 states. Yeah.
Can you iterate it? If you have 3, apply it to 2 and then apply it again?
Yeah, if you iterate it, then you end up with this equation that I wrote. But if you try to constrain 3 operators at once, then maybe you would get a different equation, or slightly different equation. But this has not been done because it looks difficult to constrain these kernels for 3 operators at once. So yeah, I'm not sure you would get a different equation. Probably you would get the same one. So these are the rules of the game. Now we can go and try to think about this, but the way progress has been achieved, okay, the way people got convinced that this is viable is by numerical analysis. So
what was the sort of numerical analysis that you can perform? You can say, you change the perspective a bit. You say, yeah, is there any question about?
Well, just maybe, I mean, at the end of the day, you want to test these things against test functions or something, right? And so then triple coincidences have essentially no contribution because that sort of lower the back measurement. I mean, you sort of see double coincidences, but you don't.
But no, I think yeah, this makes me think that I missed one point. So I'm not taking a short distance limit here. So I'm using the OP at finite separation. This is very different. So there's no singularity anywhere. So I could also do a 3-point function at finite separation and also apply OP. So that I don't think this logic applies.
Also, the kernels are singular short distances rather than smaller short
Yeah, they have some power law singularities, but again, you never look at what happens you never worry about what happens at coincident points. And actually, from the lattice point of view, it's very natural, because if you're a lattice person, you measure some correlation on the lattice. On the lattice, there are no coincident points, so why should you care about what happens, how your correlation functions behave at x equals 0? If there is some delta function there or anything, it looks like you should not care.
But in the scaling limit, you would think that the things that you're extracting is the field theory, and that field theory has singularity for coinciding points.
Yeah, but if you go to Minkowski space, of course you should care about coincident points. But in Euclidean signature, it's not obvious that you should. As a statistical physicist. Yeah. But this is a philosophical discussion. So, how was the progress achieved? It was achieved by some sort of change in perspective in a bit modest way. So you say, well, this is a very complicated equation. This equals this, infinite series of equations. I cannot clearly solve it. But let me at least try to see whether it gives some constraints on possible solutions. Like, for example, I told you that any CFT contains this list of numbers delta I. Well, can I try to deform this list of numbers? For example, can I try to push all these deltas very high and see that such a spectrum is inconsistent, that no matter what lambdas I choose, then such a CFT cannot exist? That was a kind of question that we were asking. So what I would like to do now, just to convince you that there is some room here for numerical explanation, I forgot to mention one thing. So there is one term here in this. So in this equation there are terms which are proportional to these lambdas, which we don't know. But there is one term in each of these sides that we do know, and that's the term where the exchanged operator is the unit operator. So because the OP coefficient with the unit operator is equal to 1 as a consequence of this normalization. So the fact that I normalize the 2-point function to 1 here, it means that the OP coefficient lambda I1 is equal to 1. This is just a normalization condition. So let's consider here a 4-point function of 4 identical operators. Then in each side of this equation, there is one term that we know, which is the contribution of the unit operator. And there's a bunch of terms that we don't know, contribution of everyone else. And the point is that the term which is contribution of unit operator here and here, it does not satisfy this equation by itself. It's not manifestly, it's not crossing symmetric, the term of the unit operator. So we have to add some other terms in order to restore this crossing symmetry. So that's the purpose. So you can say, what is the purpose of all the other operators in the theory? Well, from this approach, the purpose is to restore the validity of this relation because the unit operator by itself does not satisfy it. And that's how the progress initially was achieved. So you say, well, let me try to vary these deltas. If I vary these deltas, the exchange deltas here in this relation, you can look at the structure of these terms, so each of terms of this equation, and you can show by a relatively straightforward numerical analysis that if you push all the deltas above a certain limit, then all these terms, they cannot do the job. They cannot correct the crossing symmetry deficit that you have for the unit operator. And why can you show such a result? Because if all of these operators are identical, then there is some sort of positivity. You have here lambda. So let me take this operator and call it sigma. Sigma, 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 sigma. So we have here lambda, sigma, sigma, k, and here again lambda, sigma, sigma, k. So each operator, exchanged operator, enters with the square root of the OP coefficient. The sign of the OP coefficient is not known, but in unitary theories, you can show that these OP coefficients are real numbers. And so each term in these equations is positive. Well, it multiplies a certain function which is called conformal block. So this diagram is called conformal block, which is a special function. But there is some positivity there. There is some convexity there. And it's by using this kind of convexity, we realize that, well, there is some room for proving certain things. And so the business became basically we were looking for we were producing various computer-assisted proofs by analyzing the structure of conformal blocks. And what we started doing is ruling out chunks of the parameter space of conformal field theory. So I said, okay, there is deltas and lambdas, but you can rule out certain chunks. You can prove certain theorems that certain parts of this parameter space are not possible. Yeah.
Are you allowed to have negative deltas?
Very important question. So again, in non-unitary theories, yes. But in unitary theories, in reflection positive theories, there are constraints called unitarity bounds that tell you that depending on this representation, rho I, each delta has a lower bound. But these unitarity bounds are kind of known since a long time. They basically say that anomalous dimensions can be only positive. So if you take a free theory, it has scalar field has certain dimension, and in an interacting theory, which these theories are, it can only have a larger dimension. But you can show it pretty rigorously within these axioms.
I think the infrared bound statistical mechanics, right?
Yeah, I'm not familiar with this terminology, but I guess so.
Eta greater than or equal to 0.
Eta greater than or equal to 0 is an example of the infrared bound.
Yeah.
Oh, sorry, of a unitarity bound.
It is the infrared bound.
Yeah. I think, so this bound does not need conformal invariance. It's true even for scalar invariance. There are some bounds for
reflection positivity.
Reflection positivity, but there are some bounds for fields of higher spin that require also conformal invariance. Become more powerful. And okay, I mean, it went on and on, this whole business. But let me just, to show you one result which is kind of state of the art. Which is a result which applies to the three-dimensional Ising model. And this result is very instructive because in order to obtain this result, one has to analyze not just one 4-point correlation function, but several correlation functions together. And so this is the logic of this approach. So the more correlation functions you include, the more constraining power you should get, because they are correlation functions which talk to each other. So in the three-dimensional Ising model CFT, there is a Z2 symmetry, and there are two prominent scalar operators. There is one operator called sigma, which is Z2 even, Z2 odd, and there is one operator which is called epsilon, which is Z2 even. And these two operators are the only relevant operators of this theory. And this fact, you can consider it established.
Is this spin and energy?
Spin and energy, yeah, spin and energy. So this, it follows from the basic RG setup that there are no, and from experimental input, that this 3D Ising CFT describes the critical point of liquid vapor phase transition. That and since the liquid vapor phase diagram has only two directions, P and T, it means that there is no other, that there should be only two relevant operators, and this is sigma and epsilon. There are infinitely many other operators, T mu including, but these are the only two relevant ones. And so you say, well, let me study 4-point correlation functions of these two, since these two operators are clearly the most important ones. Let me study the correlation functions of sigma, of epsilon, and of sigma sigma and epsilon epsilon. So these three correlation functions. So why do you pick these three correlation functions? Well, because there is a lot of interplay between these operators. For example, in this correlation function sigma 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 sigma, epsilon is going to be exchanged. So the OPE sigma times sigma will contain the unit operator plus epsilon operator with some coefficient, which we don't know, plus it will contain T mu nu also with some coefficient which is actually can be expressed in terms of, so there is some word identity here, not unlike the one that Vieri was talking about. So there is some expression for this OPE coefficient in terms of the central charge. But there are going to be infinitely many other terms. And when you do the analysis, you allow for all these terms to appear. You don't make any, so this has really becomes a theorem. So you don't make any unjustified biased assumptions. So everything which can appear, let it appear, and it will not be able to do much, as it turns out. So the OPE epsilon times epsilon, it contains unit operator plus epsilon operator itself, plus the T mu nu, plus again dot dot dot.
Why doesn't T mu nu include the energy? I mean, wasn't that the Hamiltonian?
Well, no. It's indeed there is some terminological confusion. So we call epsilon the energy operator because when you differentiate the Hamiltonian with respect to it, you get epsilon. But epsilon is a scalar operator, and so T mu nu is a Hamiltonian, but it's how should I explain it? So perhaps I should explain how you could get T mu nu from the lattice. So how do we know that, for example, the two-dimensional Ising model, how would we measure two-dimensional Ising model T mu nu? T mu nu would correspond to deforming the Ising model to an isotropic Ising model, in which you take the coupling between the spins in the vertical and the horizontal direction not the same, while epsilon corresponds to deforming the model in the way that the couplings are deformed, all couplings are deformed together. So
I mean, T mu nu is really something like differentiating with respect to metric, right?
Respect to metric, yeah.
But that should include a time transformation, maybe not. Anyway, we can discuss this.
We can discuss this. But when you differentiate, so T mu nu has dimension d. Well, so when you and in the two-dimensional easing case, the reason why there is such an operator exists, you can understand from the fact that when you consider such an isotropic easing model, we know that there is still a critical point. So the fact that there is this critical point, that means that there exists an operator which moves you from one critical point, from isotropic to a slightly anisotropic one, and that this operator is T mu nu. Well, if you deform by epsilon, you detune from the critical point. It's a relevant direction. So it's really a different operator.
Why there are not x's in this, you know, sigma x1, sigma x2? Or
Yeah, there are, but it's just a schematic way of writing it. So.
But then it's somehow, what is this x in epsilon then, you know?
Oh, this is not x. This is a time. This is a product. Sorry, the product times. But
so then, when you write T mu nu, I mean, so the indices mu and nu, they would contract with the x's somehow?
Yeah, they would contract with so if we have here x and y, then they will contract with x minus y mu, x minus y mu.
And epsilon is at
Divided
0?
by the dimension.
Divided by some factors of x minus y for dimensional reasons.
And this e epsilon is at x minus y also? Or?
Epsilon is, you can put epsilon at x plus y over 2, for example, at the midpoint. But there's some freedom to where you put epsilon, because you can always move it and then add some derivative terms. You can do Taylor expansion. But the reason I was writing here, I wanted to point out the interplay. So sigma times epsilon, this is an interesting OPE which appears in this third correlation function. And so it contains this OPE coefficient sigma epsilon sigma times sigma. But this OPE coefficient is actually the same as sigma sigma epsilon. So the OPE coefficients are symmetric with respect to interchanging the fields you can show. And so, if you were just to consider these two correlation functions, there would not be much interplay, so you would not get much extra mileage. But with these three correlation functions, you really get a nice constraining system. And what you find is that and then you do a scan. So there are now two parameters, delta sigma and delta epsilon. And you do a scan, you pick some values for these parameters, and then you try to solve for all these lambdas and to see whether there is a consistent solution to crossing. And it's a convex optimization problem, so there are some versions of simplex method that allow you to do this. And you find that actually for most of the values of delta sigma and epsilon, solution does not exist. It exists only in some tiny region of this parameter space. So this was a numerical discovery by my colleagues. And this island, so they call it 3D easing island, it's really extremely tiny. It's, I don't know, it's like 10 to the minus 7 in extent. And the way you do it the way you do this numerical analysis is, since this is a functional equation, you cannot analyze the functional equation, so you you project it to some finite dimensional subset, and then you can increase your precision by enlarging this subset. And when you do this, this island keeps shrinking and shrinking. So for all we know, this island probably will shrink to a point. And so if this happens, then it means that an amazing thing. By using just 3 correlation functions, you are basically able to fix the 3-dimensional Ising model CFT completely. So why this happens, this is a total mystery. So
once you know delta sigma and delta epsilon, you can also construct all the other dimensions? Or
yeah, because everywhere inside this island, so when you are outside the island, there is no solution. When you are inside the island, you know that the solution exists, you can stare at it, you can extract all these coefficients and all the operators that are exchanged. So you find that the solution exists, it contains I don't know, hundreds of operators that you can stare at, and you can extract their coefficients. And you can see, when you move around the island, you can look at these operators, what they are doing. And you see that they actually don't do much. They like move a little bit when you move around the island, but they're basically stable.
So you say that you have similar constraints also on the other?
Yes. So
they all go together?
So they kind of go together, yeah. So you fix all of them in one go. So in this approach, you miraculously, so you start with these 2 parameters, delta sigma and delta epsilon, but as a bonus you get hundreds of these operators. You show that they exist. And
do these other operators have a meaning? I mean, do you know what? These are you say the subleading terms in expansion of the lattice operators or something.
Yeah, so they have this, this is the meaning that they have clearly.
Identify them or something?
Well, for example, one of these operators is the subleading operator epsilon prime, which corresponds to the subleading critical exponent, which approach to the critical point, which is people know it from the lattice, and it agrees. But there are many more. And they don't have any clear physical meaning. And in fact, what people are thinking about is to find some organizing principle for all these gazillions of operators. I mean, now there are like, for the Ising model, there's a table of 100 operators with their OPE coefficients, and what does this all mean? I don't know. This is
they have their consistency relations. They somehow shrink this.
They should have their own consistency relations, but it's not been yet fully explored. But
okay, sorry. Besides these other operators, can you once you fix delta sigma and delta epsilon, can you also compute all the higher point mixed correlations of sigma and epsilon?
You can, yeah.
So that is just a byproduct of this.
Just a byproduct, yeah.
But this sounds almost like a well-defined mathematical problem. You have this infinite hierarchy of equations, assuming, and you want to show it has a unique solution.
Yeah, absolutely. So this is like a new direction in mathematical physics, I think. There are 2 directions. You can try to work and justify the axioms of this approach. I think it's very interesting. But now, if you're just interested in critical phenomena, this is a whole new direction, because we know these equations. They are mathematically completely well defined, convergent, but we hardly understand them analytically. There's a lot of numerical work, a little bit of analytical work, but there's a lot of room for this system of equations to be understood. Okay, I should stop here.
More questions?
David?
In 2 dimensions, the same as the Yang-Baxter equations?
No, these are very different. So Yang-Baxter equations are for the scattering matrix, mostly for massive theories, integrable massive theories. So in conformal field theories, there is some attempt to use massless scattering theory, but okay, this is a murky subject. No, these are different. These crossing equations are different. This is Vieri.
There is some relation between this operator product expansion and the fact that in renormalization group you can write any non-relevant operators in terms of relevant and marginal, or it looks similar, but I don't know if it's Because in normalization, right, you express everything in terms of a few operators which are relevant or not. So is some relation, or it's just something you think is different?
No, I think it's very different. Because in normalization group sense, you know that if you perturb the UV theory by some irrelevant operator, then the IR theory is, if provided that you flow long enough, is perturbed by a handful of relevant operators, so you basically shouldn't care about irrelevant directions. But here we do care about, if you don't include these irrelevant operators in the game, you will not find a solution. You have to keep them.
You found the solution using only three of them, so all the remaining somehow.
As external operators, but inside the correlation functions, all the irrelevant guys were exchanged. Infinitely many of them. Well, in practice, we don't see infinitely many operators, we only see hundreds of operators. But we do see hundreds. And they do some beautiful things. They follow some Reggie trajectories. They have a life of their own. So it'd be nice to understand these beasts better.
Smirnov used to, there's more than one Smirnov. The Italian people used to, Musadi and other people used to write similar looking things. Is it related?
Fyodor Smirnov. I think the word bootstrap is one of the most abused words in theoretical physics. There are like gazillion bootstraps, but they also have their own bootstrap for S matrix.
Yes.
But it's of a very different kind.
So it's actually like the question I was asking about.
Yeah, I think. Yeah, no. It's a different. In fact, there is a S matrix bootstrap also.
Yeah.
But it's a different story.
But there was something in field theory. There were these current algebras. So this is that, or
I don't know, Margarita. You should tell me. So some questions I'm happy to discuss this really, but let's do it offline. Anybody else?
We use time several times.
Yeah.
So sometimes these correlations in very interesting, many cases can be written as Pfaffians. So is there a chance here that something similar could happen? There are conditions.
Well, inside there are some exactly solvable models where correlations are Pfaffians and so on. You could say, well, is this an indication that the three-dimensional Ising model CFT is exactly solvable in some sense? I don't know. One exercise that you can do, you can show using this analysis once the dust settles. You can, for example, see how the 4-point function of sigma. So sigma has a very small anomalous dimension. And so people for a long time thought that perhaps sigma is very close to a Gaussian field in some sense. But then its 4-point function has to be close to the Gaussian, fully disconnected 4-point function. But now we know the 4-point function of sigma extremely well using this approach. You can compute the ratio of the 4-point function to the Gaussian 4-point function, and you see it deviates by 30% from the Gaussian. So it's not close to the Gaussian.
Questions?
And then
Thanks.